found this in your study guide. As usual, I want to kind of look back at the outline for the whole thing. Do you have a sense of where it fits in? Really, I probably should have colored it the same as these two because it is looking at applications, but it does have some new things in it. This is kind of just a tacked on, added on thing because somebody decided you should be familiar with base E. Even though we don't really take the time in this course to really see what that number is and why it's useful, but we're going to use it for some applications, so it's going to be tied to this section, but it's not a huge deal, and I don't want you to get necessarily really stressed out about it. We've looked at applications of exponential functions. We've looked at applications of logarithmic functions. This is going to be something that is a different way or a related way of looking at applications of exponential functions, but with this base that you haven't used before. On your calculator, if you have a standard calculator of some sort, like this one, it has base 10 on it and base 10 logarithms, right? I mean, up till now, if you've had any base on there, right? 2 to the 8th, 2 to the 6th, 3 to the 4th, right? You can have, well, that was good, eh? 2 to the 63rd to the, I didn't mean to do that, but anyways, any base you want on here, right? 5 to the 6th. But there's only one so far that we've noticed that you have one logarithm you have, like one inverse for that. And the inverse is for this, right? 10 to the 4th. We have one base 10, so if I do logarithm of that number now, 10,000, it's going to give me back my original number, which is 4. You don't have any other base because you don't really need any other base. If you want to do log base 5 of something, right, of 125, if it's a number you can just figure it out, right? This happens to be a power of 5. So what is its logarithm? 3, right? If you don't know, you can always go to your calculator and use the change of base rule and just evaluate it this way. Log base 5 of 125 is log 125 over log 5, right? So you could do it that way, right? So if you ever need other bases on here of weird numbers, like if somebody puts 72 here, it's obviously not a power of 5, but you can evaluate it using the change of base rule. You can do that, right? There is one other base in your calculator, and that's what this section is about. It's base E, which seems like a weird number to have as the only other base on this calculator, especially when you see what E is, what number it is. It's a number like pi. It's an irrational number. I know when you first learned, if you think back to grade 6 or 7 or whenever you first learned about pi, probably you might have been thinking in your head, why is that such a stupid number? Like, why is it 3.141592, da-da-da-da-da? Why can't somebody just make it 3? Wouldn't that be nice if it was 3? What's the answer to that question? Why isn't it 3? Because it's not. Because it's just not, right? It would be nice if you had a circle and if you measured the diameter and then you measured the distance around. It'd be nice if the distance around was, it'd be nice if I could draw the distance around. It'd be nice if the distance around was exactly 3 times as much, but it's just not, right? It's not. It'd be nice if that was 3 times as much, but it's not. It's this many times as much, and that's just the way it is for a circle and its diameter. And it's the same thing here. It'd be nice if this was a number other than what it is. If you go to your calculator and you want to have a look at what it is, there is an E over here, and there's actually an E to the X there. So if you want to see what it is, you can either just go, if you have this kind of calculator, which I think a lot of you do, or whatever other calculator, find the E on there somewhere. That's the number. Or if you have E to the X, you can just go E and put a 1 there, right? E to the power of 1 is that number. That's what it is. You might say again, why is it that number? And the answer is, because it just is. It looks sort of like it has a pattern to it. 18281828, but it doesn't. If you had more and more decimals of this, it doesn't have a pattern. It's irrational. It just keeps going and going without a pattern, without a repeating pattern. Where it comes from, we don't have tons of time to see where it comes from here, which I hate teaching the things that way. The only reason it's in here is because someone decided that in Math 12, actually in the original Math 12 curriculum, there's no mention of E, but the people that make the provincial exam, which seem to have more authority than the original people that that designed the curriculum, put in a little statement saying Math 12 students should be familiar with the number E. Now you can interpret that any way you want, right? If it says Math 12 students should be familiar with the number E, what does that mean? Does it mean when you see this, you should be able to push the button in your calculator and see that it's roughly equal to 2.718? Or does it mean you should be able to use it? Does it mean you should be able to write equations and model things with it? We're going to kind of go somewhere in between, and we're going to say, if you're given a formula with an E in it, you shouldn't freak out. That's basically how I'm interpreting the learning outcome. When you see this letter, this variable, well, it's not a variable, when you see that number in a formula, that you don't freak out about things. Math, grade 8 students, grade 7 students, they think formulas with pi in them are harder than formulas without pi in them because it looks less familiar, right? If someone says a equals 4 times a squared, or if someone says a equals pi times a squared, which formula do you think grade 8 students think is more difficult? They think this one is more difficult. They think anything with a pi in it is harder because this is less familiar with them. That exactly the same, right? This is just a number your calculator knows, and this is going to be the same thing here. This is a number your calculator knows. I do want to give you a little tiny bit of background for where this comes from, though. I put a little box here to say where it comes from. Essentially where it comes from is if a lot of real life things, it's called natural logarithms and base E, because a lot of natural phenomenon happen where you have things that are growing continuously, or the compounding is happening instantaneously. If you think about how, compare a situation where we have interest for a bank account and a population growing. So we have interest and we have population growth here. Let's say we have $1,000 or 1,000, let's say 1,000,000. Let's make it interesting here. $1 million or 1,000,000 people, a population of 1,000,000 people. Let's say it's growing at 10%. That would be pretty huge population growth to have something that's growing at 10%. But interest over here, or growth through immigration, or babies being born and all that sort of stuff, right? Population is growing. When you're paid interest for a bank account, if you drew a graph of it, you're starting at 1,000 here, and you're starting at 1,000 over here for your population. Sorry, 1,000,000. I changed it. I forgot already that I changed it. So we're starting at 1,000,000 here, and it's going to go up from there. The population growth we've already seen. How do we model both of these with our exponential knowledge now? How do we model it? What function would we use? Y equals something times something to the power of something, right? 1,000,000 times, 110%, 1.10 to the power of x, whatever, right? The time. That's how we're modeling both of them. We're modeling both of these, but in reality, they both work slightly differently, right? The population works like this, where it grows continuously like this. Now, I might, depending on the scale I use, that might be too steep of a curve, but you get the idea. The bank account doesn't actually work like that. If we looked at individual points, it works like that, right? Like after 1 year, you might have this. After 2 years, you might have that. And 3 years, you might have this, right? And it slowly curves up like that. But in reality, you have $1 million until the end of the year when they suddenly dump the interest in, right? They're not continuously giving you the interest all year. They're not saying, oh, here's a penny, here's another penny, here's another penny. They wait till the end of the year and they put all the money in, and it suddenly jumps up to the new level. And then it stays at that level till the end of the year, and then all the interest gets dumped in at the end of the period, and so on, right? So it does kind of follow that same curve. But it doesn't, this situation, as soon as there's a new person, they're part of the population. It isn't that you wait till the end of the year and say, okay, now everybody can come in, right? Now all the babies can be born at the end of the year. As soon as they're born or they come in, they're part of the population. So it's growing continuously. Continuous growth versus kind of all at the end of the year growth. So base E has something to do with that. Really, this model is best for things like this. And we have to look at the percentage slightly differently, whether we're assuming it's continuous or not. So base E is basically thinking of, like if you took the interest situation, you could get paid more often than once a year. You could change this so that actually they compounded it more often. Even though you're getting 10% a year, that you could look after half a year, figure out 50% of the interest, 5%, and add that on. You could get paid every month, in which case you'd have dots a little bit more often here. Compound interest is getting paid more and more often. If you did it so you were compounding it continuously, as soon as there's any interest to be paid, if that gets dumped into your account, that's basically how this grows. As soon as there's any new population, it's added to the amount. So that's where this comes from. And without getting into a discussion of calculus, base E is like the limit of what happens if you compound more and more often. If you compound more and more often, it doesn't go like this. It doesn't go instantly through the roof straight up, right? You don't have an infinite amount of money. There's an upper limit. And base E comes out of that. All that being said, all I want you to be familiar with is knowing what that number is. You can go to your calculator and see what it is. If you see a formula that has an E in it, not to freak out. You might learn something about how these work here, right? On your calculator, right? If you know that e to the power of 3 is 20.0855 whatever, you should maybe know that this ln, natural logarithm, is the inverse of that. So if I go natural logarithm of 20.08553692, that's the inverse of that. Those are inverses of each other. Those two things to each other are the same as, right, these two buttons are the same to each other as these are. And I know you don't have these buttons, but if you had 2 to the x and log base 2 of x, it's the same as those things are to each other. So you can read that sometimes and see what it is. People say, you could say that this is the natural logarithm. I don't know why it's ln and not nl, but you could probably look it up on the internet and find out. Maybe it's from French or another language where the log comes first and then the natural. But people say ln x, because people are lazy. They don't want to say natural logarithm, so they just say ln x. But that's what it is. You could actually write it like this, log base e of x, if that makes more sense to you, because then it looks like everything else we've done, just a different base. That being said, then, all you're going to have to be able to do are maybe evaluate things with e in them, or if you're given a formula for something that has an e in it, be able to work with it. This is like a modeling problem that we would have done before. If we were having something that started at 25 million and you aren't given the growth rate here, but if the growth rate was 2.2%, you would model it like this. You would say y equals 25 million times 1.022 to the t. But here with base e, and you're not going to have to write these yourself. You're just going to have to be able to work with them if you're given that. I didn't give you the percentage in here. It's just given as, here's how the population's growing. So it's actually easier that way, right, for this, because you're given the formula. The only difference is you got some starting number, that's not different. You have some exponent here, that's not different. The only difference is, instead of this 1.022, it says e to the power of something. You can work with it exactly the same. You don't even need logarithms for this first question. No, you can put in this, right? Try working that out and seeing if you get a reasonable answer for that using brackets and everything. Let me pause this for a second here. Try some of these and then we're going to talk about them in a couple minutes here, okay?